Welcome to The Explainer. Every single second across our digital world, an absolutely unimaginable amount of sensitive data is flying around. We're talking about everything from your private online banking transactions to highly classified military intelligence. But, how exactly is all this information protected from adversaries as it zips across the globe? Well, we're going to decode that entire process today. We're tracing the life of a secure message, right from its foundational math all the way up to massive enterprise-level network architectures. It really all boils down to one essential question. How does a message travel safely across the globe? And figuring this out, it isn't just about memorizing a bunch of technical jargon. It's really about uncovering the hidden infrastructure of trust that literally makes our entire modern internet possible. Okay, let's dive into this. We've got a clear path today. First, we'll cover the basics of cryptography, then locking the message, looking at network blueprints, comparing the OSI and TCP/IP models, and finally, securing the modern network. Section 1. The basics of cryptography, or the art of secret writing. Let's look at how we secure data before it even touches a network. At its core, cryptography is the absolute foundation of digital trust. By taking information and scrambling it into a completely unreadable form, we make sure that only the right people can understand it. It is the silent guardian of our data, playing a vital role in protecting everything from your quick online purchases to top-tier military secrets. Modern cryptography is actually built on 4 core pillars. First is confidentiality, which just means only authorized people can read the data. Then, integrity, guaranteeing that the data hasn't been tampered with while in transit. Third is authentication, proving you're exactly who you say you are. And finally, non-repudiation. Now, this one is super fascinating. It guarantees that a sender absolutely cannot deny sending a message. Because the math provides airtight proof of origin and delivery, you can't just send a secure digital signature and later claim, hey, I never sent that. No way, the math proves you did. Moving on to part 2, locking the message. Let's introduce Alice and Bob's secret. Let's walk step by step through how Alice safely talks to Bob. First up, Alice creates her original, perfectly readable plain text message. Then, she runs it through an encryption algorithm, using a specific key to hide it. This turns the message into ciphertext, which is a totally unreadable format that's completely safe to send across the internet. When Bob gets it, he uses a key to decrypt it back into plain text. It's kind of like a giant, highly complex mathematical evolution of the ancient Caesar cipher, where they shifted letters around with a secret key, but on a massive scale. Now, what's really interesting about this is the stark trade-off we see between speed and security. In symmetric key cryptography, like AES, Alice and Bob use the exact same shared key to lock and unlock the data. It is incredibly fast, but there's a huge catch. How do they safely share that one key over an untrusted network? That's where asymmetric key cryptography, like RSA, comes in. It solves the problem by using a mathematical pair, a public key to lock the data and a private key to unlock it. It's highly secure for sure, but it is way more resource-heavy and much slower. Section 3. Network Blueprints, the rules of the road. Let's zoom out a bit. And this brilliantly illustrates the standard network blueprints we use to move all that ciphertext around. The legendary OSI model is a 7-layer conceptual framework. Think of it like a highly organized postal service. Layer 1 down at the bottom deals with raw electrical signals over cables. Moving up, Layer 3 handles IP addressing and routing, while Layer 4 ensures reliable delivery. But pay close attention to Layer 6, the presentation layer. This is the exact intersection where the cryptography we just talked about is actually applied. Data is encrypted and formatted right here before moving up to the application layer at the very top. Which brings us to Section 4, OSI versus TCP models, or theory versus practice. So while the OSI model is this nice 7-layer theoretical framework with strictly independent layers, the TCP/IP model is a 5-layer practical implementation that was actually developed by the Department of Defense. And TCP/IP is the protocol stack that runs the global internet today. Because it cares way more about practical function than strict, rigid boundaries, TCP/IP actually integrates functions, like that data formatting and encryption we just discussed, directly into its top-level application layer. All right, Section 5, Securing the Modern Network. Enter SASE. For decades, standard TCP/IP networking works like a charm because employees sat safely behind physical office walls and firewalls. But let's be real. Today, the massive shift to hybrid work and cloud computing has completely blurred those old boundaries. We're working from coffee shops, airport lounges, our living rooms. We aren't sitting safely inside a traditional network perimeter anymore, and that reality demands entirely new architectures. Enter SASE, or Secure Access Service Edge. Specifically, architectures like Prisma SASE by Palo Alto Networks. This is basically the ultimate modern solution designed to bring agility and resilience to our network connections. See, instead of forcing remote workers to route all their traffic slowly back through some central corporate headquarters just to get secured, SASE pushes the security directly out to the edge, literally right to where the user and the cloud applications actually are. It's a real game changer. So why does this matter for day-to-day operations? Well, SASE seamlessly supports today's dynamic hybrid workforces, no matter where they happen to log in from. It streamlines connectivity for retail branches without needing a bunch of clunky on-site hardware. And incredibly, it protects browser-based workspaces on any device by using secure enterprise browsers. It dynamically secures all those complex layers of the TCP/IP model we talked about earlier. But as you've probably gathered from this explainer, the journey of securing a message is never really finished. Even with brilliant architectures like SASE and robust TCP/IP protocols, the foundational cryptography we started with still faces massive hurdles. Managing, distributing, and storing all those encryption keys securely, still incredibly difficult. Then, of course, there's human error. I mean, no amount of math can save a network if an IT admin leaves the system misconfigured or if a user just chooses a terrible password. And looming right on the horizon is the ultimate technological threat: quantum computing. Here's the thing. Because quantum computers operate on entirely different laws of physics, they have the potential to one day completely shatter the complex asymmetric encryption algorithms, like RSA, that protect our digital world right now. The exact same cryptography that locks Alice and Bob's messages today might be effortlessly picked open tomorrow. It is a fascinating, never-ending arms race between codemakers and codebreakers. So I'll leave you with this. Will future quantum computers break the very foundations of the internet we just learned about?